Look up at the night sky. What do you see? Pinpricks of starlight, perhaps the soft glow of the Milky Way, the serene face of the moon. It feels peaceful, almost still. But this is a beautiful illusion. The true nature of our universe is hidden from our eyes, written in a language of light we are blind to. All around us, at every single moment, space is screaming. It is flooded with an invisible, torrential rain of the most powerful energy known to exist, gamma rays. This is the cosmic gamma ray background, a faint, omnipresent hiss of radiation that has traveled across billions of light years to reach us. It is not the light of stars, it is the echo of cosmic violence, the lingering signature of events so cataclysmic they can tear apart the fabric of space and time itself. And for decades, this background has been one of astronomy's most profound and stubborn mysteries. We are about to embark on a journey into this invisible realm to decode the screams of the cosmos. This high-energy radiation holds the secrets to the most extreme and violent phenomena imaginable. It whispers tales from an era before the first stars were born, carrying information from the edges of black holes where gravity becomes infinite and from collisions of entire galaxies. Every photon in this background is a messenger, but we are only just learning how to listen. What could possibly generate such a constant, pervasive bath of energy? Are we hearing the collective roar of distant, unknown objects, or is it the signature of something far more exotic, perhaps even evidence of dark matter annihilating itself in the void? In this video, we will unravel 25 specific, mind-bending mysteries tied to this enigmatic signal. We will explore the desperate hunt by astronomers to pinpoint its origins, a pursuit that pushes our telescopes to their absolute limits and challenges our fundamental understanding of physics. From the death cries of massive stars to the possibility of cracks in the laws of the universe as we know them, each mystery pulls us deeper into the cosmic unknown. This is not just a story about light we cannot see. It is a story about our quest to understand the true, chaotic, and magnificent nature of reality itself. So let's begin. Our first and perhaps most fundamental mystery begins with a simple, profound question. Where is all this energy coming from? The gamma ray background isn't a collection of sharp, distinct points of light like stars in a familiar constellation. Instead, it manifests as an incredibly smooth, diffuse glow, a near-uniform fog of energy that envelops the entire cosmos. This smoothness is the heart of the puzzle. If it were made of individual sources we could count like distant lighthouses, their combined light would create a speckled, uneven map. The fact that it is so uniform tells us we are likely hearing a cosmic chorus, a collective roar from an immense number of faint, distant objects whose individual voices blend into a single, seamless hum. The leading suspects in this cosmic choir are some of the most powerful engines in the universe, active galactic nuclei, or a GN. At the heart of many galaxies, including our own Milky Way, lies a supermassive black hole. But in an AGN, this black hole is actively feasting on surrounding gas and dust. As material spirals into the abyss, it heats up to incredible temperatures, and in a final act of defiance before being swallowed, it shoots out colossal jets of particles and radiation traveling at nearly the speed of light. When one of these jets is pointed directly at Earth, we call that specific type of a GN a blazar. Blazars are among the brightest persistent gamma ray sources in the sky. So the prevailing theory is quite logical. The diffuse gamma ray glow is simply the combined light of every single blazar and other active galaxy in the observable universe. Their individual signals too faint for our telescopes to see individually, but together creating a detectable background. This is where the mystery deepens considerably. Our most powerful eye on this high-energy universe, the Fermi Gamma Ray Space Telescope, has been meticulously mapping the sky for over a decade. It has catalogued thousands of these brilliant blazars, Scientists have taken this catalog and built sophisticated models, essentially asking, if we add up the light from every blazar we can see, and then extrapolate to account for the countless more that are too far away for Fermi to resolve, does it equal the intensity of the diffuse glow we actually measure? The answer consistently is no. There is a significant gap. The combined light of all these monstrous engines, according to our best calculations, still falls short of explaining the full intensity of the background. This means one of two thrilling possibilities must be true. Either our census of these celestial monsters is still incomplete, and the universe contains a much larger population of faint, hidden blazars than we ever predicted, lurking just beyond the detection threshold of our finest instruments. Or, and this is the more provocative idea, there is an entirely different, unknown source contributing to this signal. Something else, something pervasive and powerful, is also flooding the universe with gamma rays. This discrepancy forces us to look beyond the known, to consider if we are missing a fundamental piece of the cosmic puzzle. The smooth glow is not just a simple sum of known parts, it is a clue pointing toward phenomena we have yet to even imagine. This leads us directly into our second great mystery, often called the blazar paradox. To solve the puzzle of the missing gamma rays, astronomers turn to a powerful statistical tool known as the luminosity function. Think of it like a cosmic census. By studying the blazars we can see, the bright, nearby ones, scientists can create a model that predicts how many fainter, more distant ones should be out there. It's similar to knowing that in any given city, for every skyscraper there are many more smaller office buildings and houses. The luminosity function tells us the demographics of the universe's gamma ray sources. It estimates the relative numbers of the brilliant beacons versus the countless dimmer emitters that should fill in the gaps. The paradox emerges when we compare this prediction to the actual, measured glow of the background. The collective light from the blazars we've already identified, plus the vast number of faint ones predicted by the luminosity function, still does not add up to the total signal we observe. It's as if we've counted every person we can see in a gigantic, crowded stadium, and then used that count to estimate the total attendance, only to find that the roar of the crowd is far louder than our head count can explain. This means we are faced with two equally fascinating possibilities. The first is that our census is fundamentally incomplete. There could exist an entire population of stealth blazars that our current telescopes are simply not designed to find. These might be black holes with jets pointed just slightly away from our line of sight, making them appear much dimmer, or they could be ancient, dying engines from the early universe whose light has been stretched and faded over billions of years. Finding this missing population would revolutionize our understanding of how supermassive black holes grow and evolve across cosmic time. The second, more radical possibility is that our understanding of the blazars themselves is flawed. Perhaps the models we use to calculate how much gamma radiation these jets produce are incorrect. Maybe under certain conditions, such as in environments with incredibly strong magnetic fields or with different compositions of infalling material, these cosmic engines operate in ways we haven't yet predicted, generating more high-energy light than our current physics allows for. This wouldn't just mean we're missing some objects, it would mean we don't fully understand the objects we've already found. The implications of this blazar paradox ripple outward, touching on one of the grandest questions in astronomy. How did the supermassive black holes at the hearts of galaxies get so immense? If there is a vast, hidden population of them, it suggests that the growth of these gravitational monsters was even more prolific in the early universe than we thought. Alternatively, if our models are wrong, we may need to rethink the very mechanisms that power the most energetic and persistent phenomena in the cosmos. The smooth gamma-ray glow is therefore more than just a light in the dark. It is a precise measuring tool, and right now, it's telling us that our ledger of the universe's most violent events does not balance. But if the brightest monsters in the cosmos cannot fully account for the gamma-ray fog, perhaps we have been overlooking the collective murmur of countless ordinary galaxies. This brings us to our third mystery, the potential role of star-forming galaxies. Unlike the dramatic, jet-powered active galactic nuclei, these are the universe's steady, productive workhorses. Galaxies like our own Milky Way are not quiet. They are bustling with the birth and death of stars, and all this stellar activity generates a pervasive, invisible sea of high-energy particles called cosmic rays. Protons and atomic nuclei, accelerated to nearly the speed of light by supernova explosions and stellar winds, constantly zip through the interstellar medium. It is within this chaotic environment that a secondary but significant source of gamma rays is born. The process begins when these ultra-fast cosmic ray protons smash into the slower, colder protons of the interstellar gas. These violent proton-proton collisions can create short-lived particles called pions, which almost immediately decay into gamma rays. It's a bit like the constant, faint crackle of static from a radio, generated by countless tiny electrical discharges rather than the focused blast of a spotlight. At the same time, another process is at work. The universe is filled with light starlight, infrared glow from dust, and the ancient echo of the Big Bang itself, the cosmic microwave background. When cosmic ray electrons, also accelerated by stellar violence, collide with these low-energy photons, they can transfer a tremendous amount of energy to them in a process known as inverse Compton scattering. This effectively takes a gentle whisper of light and supercharges it, boosting it all the way up into the gamma-ray part of the spectrum. So, within every actively star-forming galaxy, there is a constant, low-level production of gamma rays happening everywhere, a byproduct of its normal, turbulent life. The crucial question is whether the combined output from every such galaxy in the universe adds up to a significant portion of the mysterious background. The challenge in answering this is immense. While our Fermi telescope can easily detect the powerful gamma-ray signal from a blazar billions of light-years away, it struggles to see the faint, diffuse glow from a normal galaxy even in our own cosmic neighborhood. We have only managed to detect this emission from a handful of the very closest star-forming galaxies. To understand their total contribution, we are forced to study these nearby examples in extreme detail and then extrapolate, assuming that galaxies in the distant past behaved in a similar way. This is a huge uncertainty. The early universe was a much more violent and fertile place for star formation. Galaxies back then were likely churning out stars at a ferocious rate, which would have meant more supernova, more cosmic rays, and consequently, a much brighter gamma-ray glow from each one. If this is the case, the combined light from these countless normal galaxies could indeed be the missing piece of the puzzle, quietly making up the deficit that the blazars alone cannot cover. However, proving this is a monumental task. It requires not only more sensitive telescopes, but also a deeper understanding of how cosmic rays are generated and confined within galaxies across billions of years of cosmic history. The faint, steady hum of star-forming galaxies represents a background chorus to the universe's violent solos, and determining the volume of that chorus is one of the most pressing challenges in high-energy astrophysics. If the combined roar of black holes and the steady hum of star formation still leaves us with unanswered questions, then we must turn our attention to the most elusive substance in the cosmos, dark matter. This brings us to our fourth and perhaps most profound mystery. The gamma-ray background could be more than just an astrophysical signal. It might be the long-sought-after evidence of dark matter particles annihilating each other in the vast emptiness of space. Think about that for a moment. The invisible fog surrounding us might not just be hiding the universe's secrets. It could be the secret itself, the visible echo of the invisible. The theoretical foundation for this incredible idea rests on a leading candidate for what dark matter could be, weakly interacting massive particles, or WIMP. As the name suggests, these are hypothetical particles that have mass and interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect directly. But according to some theories, when two WIMP collide, they could annihilate each other in a flash of energy, transforming into particles we know and can detect, such as electrons, positrons, and most importantly for our story, gamma rays. If this is happening, then every corner of the universe where dark matter congregates should be glowing faintly with this high-energy light. The gamma ray background, which appears so smooth and uniform, could be the cumulative glow from trillions upon trillions of these tiny annihilations occurring in dark matter halos around every galaxy and in the vast, empty spaces between them. This is why astronomers are not just looking for a general excess of gamma rays. They are hunting for a very specific telltale signature in the background's energy spectrum. Imagine listening to a radio filled with static. You're trying to pick out one specific musical note that is played over and over again. Similarly, different physical processes produce gamma rays with characteristic energies. The annihilation of a specific type of WIMP would theoretically produce a sharp spike or a distinct bump at a particular energy level in the otherwise smooth continuum of the gamma ray background. Finding such a line would be the smoking gun, an unambiguous fingerprint left by dark matter. The diffuse nature of the background is both the great promise and the immense challenge of this search. On one hand, it's promising because dark matter is thought to be everywhere, not clumped in just a few bright points. Its signal should be widespread and smooth, just like the background we observe. It effectively gives us the largest possible detector imaginable, the entire universe. We can look toward the center of our own Milky Way, where dark matter is believed to be most dense, or toward other galaxies, searching for this faint, pervasive glow. The challenge, however, is that this signal is incredibly weak and buried under the astrophysical noise from all the blazars and star-forming galaxies we've already discussed. Teasing apart a potential dark matter signal from the collective emission of these known sources is like trying to hear a single person whispering in a roaring stadium. It requires exquisitely precise models of all other gamma-ray contributors. Any error in our understanding of blazar populations or cosmic ray processes could create a false bump in the data that mimics a dark matter signal. This has led to decades of tantalizing hints and frustrating dead ends. Certain anomalies, like an unexpected excess of gamma rays from the galactic center, have sparked excitement, but have so far been explained by more conventional sources, such as a previously unknown population of rapidly spinning neutron stars called pulsars. The hunt continues, growing ever more sophisticated, because the potential reward is nothing less than a fundamental rewriting of the laws of physics and a final answer to one of science's greatest questions. As we peel back the layers of the gamma ray background, the plot thickens in a very specific and unexpected way. When scientists analyze the energy of these photons, they don't just see a smooth decline from low to high energies. Instead, they find a curious bump, a persistent excess of gamma rays at the very highest energies, above about 1 giga-electronvolt. This isn't a subtle discrepancy, it's a glaring anomaly that stands out in the data. Imagine you're listening to a complex symphony, and you expect the volume of the violins, cellos, and brass sections to blend in a predictable way. But as the music reaches its crescendo, the piccolo section is playing far louder than the composer's score indicates. That's the high-energy excess, a section of the cosmic orchestra that is overpowering its predicted role. This observation pushes us into a fascinating theoretical battleground. The first and most conservative explanation is that our models of known sources are simply incomplete at these extreme energies. Perhaps blazars, when they flare, produce a higher proportion of very high-energy gamma rays than our current simulations account for. It's possible that the environments around these supermassive black holes accelerate particles in ways we haven't yet fully understood, leading to a harder, more energetic spectrum of radiation. Similarly, the processes within star-forming galaxies might be more efficient at generating high-energy gamma rays than we think. Cosmic rays accelerated by supernova remnants could be interacting with interstellar material in more complex ways, creating a surplus at the top end of the energy scale. This line of investigation forces astronomers to refine their understanding of these extreme engines, tweaking the physics to see if they can make the known universe account for this anomalous signal. However, if these astrophysical adjustments consistently fail to explain the excess, we are forced to consider far more thrilling possibilities. This bump in the data could be a direct window into new physics. One compelling idea brings us back to dark matter, but with a twist. The standard WIMP models often predict annihilation signals at lower energies. But what if dark matter is composed of heavier, more massive particles? These so-called heavy dark matter candidates, with masses thousands of times greater than a proton, would naturally annihilate to produce gamma rays at much higher energies, potentially right in the range where we see this puzzling excess. The smooth, isotropic nature of the background would be a perfect match for a signal originating from dark matter halos across the cosmos. Finding this correlation would be a monumental breakthrough, not just identifying dark matter, but also revealing its specific properties and mass. Beyond dark matter, the high-energy excess opens the door to even more exotic phenomena. Could it be evidence of the decay of primordial black holes, tiny remnants from the Big Bang era that are evaporating in a final burst of high-energy radiation? Or perhaps it's a signature of cosmic strings, hypothetical topological defects in the fabric of spacetime, left over from the early universe, whose vibrations could release tremendous energy. Some theorists have even explored whether it could be related to actions, another hypothetical particle that could convert into gamma rays in the presence of strong magnetic fields. Each of these ideas represents a radical departure from standard astrophysics, suggesting that the gamma-ray background is not just a collection of known objects, but a canvas for fundamental physical processes we are only beginning to imagine. Resolving this mystery falls to our most powerful observatories, chief among them the Fermi Large Area Telescope, or LAT. Fermi's mission is to constantly scan the entire sky, collecting billions of gamma-ray events over many years. The key to unlocking the high-energy excess lies in this sheer volume of data. With each passing year, the statistics improve, allowing scientists to measure the spectrum with ever greater precision and reduce the uncertainties that cloud our interpretation. The goal is to see if the excess remains a stubborn feature as the data gets cleaner, or if it gradually smooths out into the predicted curve. Furthermore, Fermi isn't just measuring energy, it's also measuring the arrival direction of each photon. By creating incredibly detailed maps of the sky at these specific high energies, astronomers can try to see if the excess is correlated with known structures, like the plane of our Milky Way galaxy or the locations of massive galaxy clusters, which would point toward an astrophysical origin. If, however, the excess remains perfectly smooth and uniform across the sky, it would significantly strengthen the case for a truly diffuse source like dark matter. The hunt is a painstaking process of elimination, a meticulous effort to rule out every conceivable astrophysical contributor until only the most extraordinary explanations remain. This high-energy anomaly is more than just a data point. It is a direct challenge, a signal from the universe that our current catalogue of cosmic phenomena is still missing some of its most powerful members. Now, if distant galaxies and exotic particles aren't the whole story, we must turn our gaze to the very architecture of the cosmos itself, the immense networks of galaxy clusters. These are not just random groups of stars, they are the universe's largest gravitationally bound structures, the metropolises where thousands of galaxies are drawn together by the irresistible pull of dark matter. Within these vast cosmic assemblies, a more subtle and sustained process could be generating gamma rays, contributing its own unique whisper to the background hum. The key player here isn't just the galaxies, but the incredible sea of superheated gas that fills the space between them. This intracluster medium is so hot that it glows in X-rays, and it's threaded by powerful magnetic fields. This environment becomes a perfect natural particle accelerator. When galaxies within a cluster undergo star formation or host active black holes, they inject cosmic rays into this communal pool. Once these high-energy particles enter the cluster's realm, they are effectively trapped. The tangled magnetic fields act like a cage, causing the cosmic rays to bounce around for millions of years, far longer than they could survive within a single galaxy. During this immense imprisonment, these particles have countless opportunities to collide with the protons in the hot gas or with the photons of background light. Each of these collisions is a chance to produce a gamma ray. This means a single galaxy cluster isn't just a momentary source of high-energy light. It's a long-lived, efficient factory, steadily converting the energy of cosmic rays into gamma radiation over cosmic timescales. The challenge and the heart of this mystery lies in the sheer difficulty of detecting this specific emission. For any single cluster, the predicted gamma ray signal is exceedingly faint. Our telescopes, like Fermi, are straining at their absolute limits to see it. We have tentative detections from a handful of the very closest and most massive clusters, but these are just the tip of the iceberg. The vast majority of clusters in the universe are simply too far away for their individual gamma ray glow to be distinguished from the general background noise. This leads to a fascinating and plausible idea. What if we cannot see the trees, but we are hearing the rustle of the entire forest? The unresolved, collective glow from every galaxy cluster in the observable universe could be seamlessly blended into the isotropic gamma ray background. It would be a diffuse signal born from diffuse sources, a perfect match for the smooth fog we observe. Calculating the exact contribution of this cosmic chorus is incredibly complex. It depends on factors we are still trying to measure, such as the efficiency with which clusters trap cosmic rays and the exact strength of their magnetic fields. If clusters are even slightly more effective at this process than our conservative estimates suggest, their combined output could represent a significant and previously overlooked piece of the puzzle. This forces us to see the large-scale universe not just as a collection of points of light, but as an interconnected web where the empty spaces between galaxies are teeming with physical activity, contributing their own distinct voice to the symphony of the gamma-ray sky. But to truly listen to the whispers of the distant cosmos, we must first understand the medium through which they travel. This brings us to a particularly elegant and complex mystery, one that turns an obstacle into a tool. The universe, it turns out, is not perfectly transparent to gamma rays. For these high-energy photons attempting to cross billions of light years, space itself has a kind of fog. This fog is the extragalactic background light, or EBL, and its interaction with gamma rays holds a hidden key to measuring cosmic history. Imagine you're trying to see the beam of a distant lighthouse through a thick, patchy mist. Some of the light gets through, but the brighter, more intense beams are scattered and absorbed by the water droplets in the air. A similar process happens on a cosmic scale. The EBL is the cumulative glow of all the starlight ever emitted throughout the history of the universe, from the first brilliant, massive stars to the gentle shine of countless suns like our own. It also includes the infrared light radiated by dust that has been warmed by that starlight. This ancient light doesn't just disappear, it fills the entire cosmos with a sea of low-energy photons, a fossil record of every star that has ever shined. When a high-energy gamma ray, born from a cataclysm in a faraway galaxy, happens to collide with one of these EBL photons, something remarkable occurs. If the gamma ray has enough energy, the collision can create matter, According to Einstein's famous equation, energy can be converted into mass, and in this specific case, the collision produces an electron and its antimatter counterpart, a positron. In that instant, both the original gamma ray and the EBL photon are gone, their energy transformed into new particles. The gamma ray has effectively been absorbed, its journey cut short. This process, known as pair production, acts like a cosmic filter. It means the universe becomes increasingly opaque to the highest energy gamma rays the farther they have to travel. A gamma ray from a relatively nearby source has a good chance of reaching us, but a gamma ray of the same energy from a source halfway across the observable universe is far more likely to be absorbed along the way. This absorption leaves a very specific imprint on the gamma ray background spectrum that we measure here at Earth. As we look at higher and higher gamma ray energies, we expect to see fewer and fewer photons from the most distant reaches of space. The spectrum doesn't just smoothly decline, it has a predictable absorption horizon that depends on the density and nature of the EBL itself. This is where the obstacle becomes a powerful probe. The amount of absorption tells us about the thickness of the fog. By carefully analyzing how the gamma ray spectrum from distant blazars is softened or attenuated, scientists can work backwards to measure the total amount of EBL that the photons encountered on their journey. In essence, we are using gamma rays as a kind of cosmic dipstick to measure the total reservoir of starlight in the universe. This provides an independent and crucial check on our understanding of galaxy evolution. We can compare the EBL density measured by gamma ray absorption to the EBL. We estimate by counting all the galaxies we can see in deep field observations with telescopes like Hubble and James Webb. If the two measurements agree, it gives us tremendous confidence that our census of galaxies and our models of star formation across cosmic time are largely correct. However, any discrepancy would be explosive. If the gamma ray method suggests a denser EBL than our galaxy counts can account for, it could mean there is a missing population of very faint, early galaxies whose combined starlight we have not yet detected, shining from an era right after the Big Bang. The gamma ray background, therefore, is not just a signal to be decoded. It is an active instrument allowing us to peer back through time and take an inventory of all the light ever produced, using the most violent events in the present to illuminate the quiet, accumulated glow of the past. Shifting our focus from the largest structures in the universe to the remnants of individual stellar deaths, we arrive at a mystery powered by the universe's most precise clocks, pulsars. These are the ultra-dense, rapidly spinning cores left behind after a massive star goes supernova. A pulsar is a city-sized ball of neutrons, so incredibly dense that a single teaspoon of its material would weigh billions of tons. As this cosmic cinder spins, sometimes hundreds of times per second, its immense magnetic field acts like a colossal lighthouse beacon, funneling intense radiation into narrow beams that sweep across the sky. If one of those beams happens to point toward Earth, we see a regular, rapid-fire pulse of light. And for some pulsars, that light is not just visible or radio waves, it is a powerful beam of gamma rays. Our own Milky Way galaxy is home to a growing catalog of these gamma-ray pulsars discovered by the Fermi telescope. They are astonishingly efficient engines, converting their rotational energy, the energy of their spin, directly into high-energy radiation. This leads to a compelling and elegant idea. If our galaxy has a population of these gamma-ray emitting pulsars, then surely every other galaxy does too. Could the combined, unresolved light from all the pulsars in all the galaxies across the cosmos be a major contributor to the diffuse gamma-ray background? Instead of a roar from monstrous black holes, the background could be, in part, a collective hum from countless dead stars, each spinning silently in the dark. The challenge in answering this lies in the unresolved nature of the signal. We can see the bright, individual pulsars in our own galactic neighborhood, but we cannot hope to detect a single pulsar in a distant galaxy. Their light is simply too faint, so we are forced to become cosmic demographers. We study the pulsar population we know, their ages, their spin rates, their magnetic field strengths, and how brightly they shine in gamma rays, and we build a model to predict how many should exist in a typical galaxy. We then multiply that by the countless galaxies in the universe and add up their predicted gamma ray glow. The results of this exercise are tantalizing but uncertain. Some studies suggest that pulsars could indeed account for a substantial fraction, perhaps even more than 10%, of the entire gamma ray background, particularly at certain energy ranges. Other models are more conservative, assigning them a smaller role. The greatest uncertainty revolves around the life cycle of a pulsar. A young pulsar spins rapidly and is a brilliant source of gamma rays. But over millions of years, it gradually slows down, its pulses becoming weaker and wider apart until it eventually fades into obscurity. The critical question is, how does a pulsar's gamma ray luminosity evolve over its lifetime? Do they shine brightly for a long time, or is their high-energy youth relatively brief? If they are long-lived gamma ray emitters, then the universe would be filled with a vast, faint population of middle-aged pulsars whose combined light could be immense. Furthermore, we have to consider the early universe. Galaxies were closer together and forming stars at a much higher rate. This means there would have been more supernova, creating more pulsars in a smaller volume of space. The pulsar background from billions of years ago might have been significantly brighter than it is today. Estimating this contribution requires us to not only understand pulsar physics, but also to have an accurate picture of the star-forming history of the entire cosmos. The faint, steady glow of these cosmic lighthouses represents a background hum that is incredibly difficult to distinguish from the other signals, but it remains a persistent and plausible voice in the gamma ray chorus, a reminder that the end of a star's life can create an engine that illuminates the universe long after the star itself is gone. While we often think of the violent universe in terms of persistent monsters like blazars, some of its most dramatic events are incredibly brief, fleeting cataclysms that vanish in the blink of a cosmic eye. This brings us to the controversial and fascinating possibility that the gamma ray background carries the faint, collective echo of the most powerful explosion since the Big Bang, gamma ray bursts or GRBS. A single GRB can, for just a few seconds, outshine every star in every galaxy in the observable universe combined. They are the ultimate cosmic flashbulbs, signaling the birth of a black hole from the collapse of a massive star or the merger of two ultra-dense neutron stars. But what happens after the main flash? The story doesn't end there. The initial blast is followed by a long-lived multi-wavelength afterglow that can linger for days, weeks, or even months, fading gradually across the electromagnetic spectrum from gamma rays down to radio waves. This afterglow is created as the jet of material hurtling outward from the explosion slams into the surrounding interstellar gas at nearly the speed of light, creating a shock wave that acts like a natural particle accelerator, causing the gas to glow brightly. Now consider the sheer scale of cosmic history. Billions of years have passed, and in that time, an immense number of these spectacular explosions have occurred in galaxies across the cosmos. Each one left behind its own fading ember of an afterglow. While any single afterglow is transient, the universe is so vast and so old that at any given moment, the sky should be filled with the incredibly faint, overlapping afterglows of countless GRBS that have exploded at different times in the past. It's akin to being in a vast stadium where flashbulbs are constantly popping off at random. At any single instant, you see a few bright, recent flashes. But if you could take a long exposure photograph, the entire scene would be bathed in a soft, pervasive glow from the accumulated light of every flash that occurred during the exposure. The gamma ray background could be that long exposure photograph of the universe, with the high energy component of all those afterglows blending into a permanent, diffuse mark. The calculations behind this idea are as complex as they are compelling. Astrophysicists have developed sophisticated models based on the observed rates of GRBS, their typical energies, and the physics of how their afterglows evolve over time. They essentially ask a grand statistical question. If we add up the gamma ray light from the afterglow phase of every single GRB that has ever occurred and smear that light across the entire sky, what would the total intensity be? The results suggest that while this contribution is likely small, it could indeed be detectable as a distinct component within the overall background. It would not be a dominant source, but rather a subtle signature superimposed on the louder roar from blazars and star-forming galaxies. The key to identifying it lies in its unique characteristics. Unlike the steady emission from an active galaxy, the GRB afterglow component would have a specific spectral shape, a fingerprint dictated by the physics of shock, acceleration, and radiation. Furthermore, because the rate of GRBS is thought to have been much higher in the early universe when massive stars were forming at a frantic pace, this fossil glow might carry a specific energy signature that reflects that ancient, more violent era. Detecting this faint signal, however, is a monumental challenge. It is buried deep within the much brighter diffuse emission from other sources. Isolating it requires an exquisitely precise understanding of all the other contributors, which we are still refining. Yet the scientific payoff for succeeding would be extraordinary. This persistent glow would act as a unique fossil record, a kind of cosmic sediment layer preserving the history of stellar death on a grand scale. By analyzing its properties, we could learn about the average properties of GRBS throughout cosmic time, how energetic they typically were, how their jets interacted with their environments, and even how their rate has changed over billions of years. It would provide a way to study these magnificent explosions not just as individual, rare events that we are lucky to catch, but as a population that has fundamentally shaped the universe. This transforms the gamma ray background from a simple puzzle to be solved into a potential time capsule, holding the faded echoes of the universe's most brilliant and destructive moments. Beyond the dazzling explosions and the steady glow of galaxies, the universe is constantly being reshaped by forces on the grandest scale imaginable. To uncover our next mystery, we must zoom out to view the cosmos in its entirety, observing the slow, majestic choreography that has been unfolding for over 13 billion years. This is the process of large-scale structure formation, and it is far from a gentle affair. The gravitational pull of dark matter has been drawing ordinary matter into an immense cosmic web, a network of filaments and sheets connecting vast hubs where thousands of galaxies cluster together. As vast rivers of primordial gas flow along these filaments, drawn inexorably toward the dense clusters at the intersections, they do not glide smoothly. Instead, they crash into the gas already collected there at speeds of thousands of kilometers per second. These collisions generate the largest shock waves in the universe, titanic walls of energy that ripple through intergalactic space for millions of light years. These are not mere sonic booms, they are cosmological tsunamis, and they represent a formidable, universe-wide engine for generating gamma rays. Within these colossal shock fronts, a fundamental physical process unfolds with breathtaking efficiency. The same mechanism that accelerates particles in a supernova remnant or a pulsar wind nebula operates here, but on a truly epic scale. As the supersonic flow of gas slams into the relatively stationary plasma of a galaxy cluster, it creates a chaotic, magnetized boundary. Protons and electrons caught in this turmoil can be trapped, bouncing back and forth across the shock wave. With each crossing, the magnetic fields of the shock transfer a little more energy to them, like a vast natural particle accelerator. After many crossings, some of these particles are boosted to velocities approaching the speed of light, becoming ultra-high-energy cosmic rays. Once accelerated, these particles are then set loose within the immense volumes of the cosmic web. It is here that the final step to gamma ray production occurs. the relativistic protons collide with the much slower, colder protons in the surrounding gas. These violent impacts create unstable particles called neutral pions, which decay almost instantly into pairs of gamma-ray photons. This process transforms the kinetic energy of gravitational infall, the sheer motion of gas falling into a cluster, into the high-energy light that forms part of the universal background. The profound question is whether the combined output from every one of these cosmic construction sites throughout time adds up to a significant portion of the signal we observe. The key factor is pervasiveness. While a single structure formation shock is immense, its gamma-ray emission per unit volume is incredibly faint, spread across such a vast area that it would be undetectable as an individual object. However, this process is not rare. It is the fundamental method by which all clusters and superclusters of galaxies are built. Billions of years ago, when the universe was smaller and denser, this activity was even more intense. Shock waves would have been a ubiquitous feature of the young cosmos, occurring wherever the first large structures were collapsing. This means that the gamma rays produced by these events would not come from distinct points on the sky, but would instead form a truly diffuse isotropic glow, perfectly matching the smooth character of the gamma ray background. Calculating this total contribution is a frontier of computational cosmology. Scientists run massive simulations of the universe's evolution, modeling the growth of the dark matter web and the flow of gas along it. These simulations track where and when these gigantic shocks form, and then estimate the amount of particle acceleration and subsequent gamma-ray emission. The results suggest that this could indeed be a measurable component, a fossil imprint of the universe's violent architectural phase. It represents a background hum that is fundamentally different from the point source emission of galaxies or black holes. It is the sound of the cosmos being built, the faint, high-energy echo of the universe assembling its largest structures under the relentless pull of gravity. To truly understand the gamma-ray sky, we sometimes have to listen to the universe on a different channel. This brings us to a particularly intriguing clue: the mysterious connection between the gamma-ray background and a similar, unresolved fog at the other end of the electromagnetic spectrum, the radio wave background. It turns out that the cosmos isn't just screaming in gamma rays, it's also humming a steady, low-frequency tune. These two backgrounds, one representing the highest energies and the other some of the lowest, share a surprising characteristic. They are both remarkably smooth and isotropic, appearing nearly the same in every direction. This isn't likely a coincidence. The correlation suggests that these two signals, seemingly worlds apart, might be different manifestations of the same underlying cosmic phenomena. It's as if we've found two separate pieces of sheet music that, when played together, create a harmonious chord pointing toward a common origin. The most promising candidate for this shared source brings us back to the bustling, star-forming galaxies we discussed earlier. These galaxies are not just factories for gamma rays, they are also prolific generators of radio waves. The connection lies in a specific type of particle found zipping through their interstellar medium, cosmic ray electrons. When these high-speed electrons spiral along the magnetic field lines that are woven throughout a galaxy, they emit a very particular kind of radiation known as synchrotron radiation. This process is incredibly efficient at producing radio waves, so within a single star-forming galaxy, you have two powerful, non-thermal processes occurring simultaneously. Cosmic ray protons collide with gas to produce gamma rays, while cosmic ray electrons interacting with magnetic fields generate the radio glow. If the unresolved gamma ray background is indeed the combined light from all the star-forming galaxies in the universe, then it makes perfect sense that we would also see a correspondingly smooth radio background from those exact same galaxies. The two signals would be intrinsically linked, two different products of the same violent stellar life cycle. However, the plot thickens considerably when we look deeper. While star-forming galaxies are a strong contender, they are not the only objects that produce both gamma rays and radio waves. Another prime suspect is the population of active galactic nuclei, particularly those with powerful jets. The same relativistic jets that generate gamma rays through various processes are also brilliant sources of synchrotron radio emission. Could the unresolved background be a mix, with blazars dominating the gamma ray side and star-forming galaxies contributing more to the radio, or vice versa? Disentangling this requires the powerful toolkit of multi-wavelength astronomy. By observing the same patch of sky with gamma-ray telescopes like Fermi, radio telescopes like the Low-Frequency Array or LOFAR, and optical telescopes like Hubble, astronomers can build a complete energy portrait of the universe. They can identify the specific types of galaxies that are responsible for the parts of the background we can resolve, and then use that knowledge to build a statistical model for the trillions of sources we cannot see individually. The radio data acts as a crucial cross-check. If a model proposes that a certain population of faint star-forming galaxies explains the gamma-ray background, that same population must also be able to account for the observed radio background. If it fails to do so, the model must be revised. This multi-wavelength approach is revealing something profound about the universe's fundamental workings. The correlation between the gamma-ray and radio backgrounds is a direct probe of non-thermal processes phenomena that are not simply about heat, but about acceleration and extreme physics. It tells us that the universe is filled with natural particle accelerators, from the shock waves of supernova remnants to the jets of supermassive black holes. The relative strength of the gamma-ray signal compared to the radio signal gives us clues about the efficiency of these accelerators. For instance, it can tell us about the ratio of cosmic ray protons to cosmic ray electrons being produced, which is a key detail in understanding the mechanics of stellar explosions and jet formation. A universe where the gamma-ray background is much stronger relative to the radio background might be one where proton acceleration is particularly efficient, perhaps pointing toward environments with stronger magnetic fields or more violent shocks. Therefore, this connection is far more than just a convenient correlation. It is a measuring stick for the high-energy physics that governs the most dynamic environments across cosmic time, allowing us to hear the same cosmic story told in two very different but deeply connected languages. Now we turn to one of the most fascinating and speculative ideas in all of theoretical physics, a concept that connects the very smallest scales of quantum mechanics to the grandest cosmic mysteries, the potential role of primordial black holes. To understand this, we have to journey back to the very first moments after the Big Bang. The newborn universe was not perfectly smooth. It was a seething, turbulent sea of energy, dense beyond comprehension. In such extreme conditions, theorists propose that random fluctuations in density could have collapsed under their own gravity, not into stars or galaxies, but directly into black holes. Unlike the stellar mass black holes formed from dying stars or the supermassive ones anchoring galaxies, these primordial black holes could have been forged in any size, from the mass of a small asteroid to many times the mass of our Sun. And crucially, some of them could have been incredibly tiny. This is where Stephen Hawking's revolutionary insight comes into play. Classical physics told us that black holes are eternal, that nothing, not even light, can escape their gravitational grip. But Hawking realized that when you introduce the strange rules of quantum mechanics near the event horizon, this is not entirely true. He proposed that black holes can actually evaporate, slowly leaking radiation over astronomical timescales. The mechanism is mind-bending. According to quantum theory, empty space is not truly empty. It is a frothing sea of virtual particles, pairs of particles and antiparticles that spontaneously pop into existence and then almost instantly annihilate each other. Hawking suggested that if this particle-antiparticle pair appears right at the edge of a black hole's event horizon, one particle might fall in while the other escapes. From the perspective of a distant observer, the black hole has just emitted a particle. This is Hawking radiation. For a massive black hole like the one at the center of our galaxy, this process is incredibly slow, producing a feeble trickle of radiation so faint it's completely undetectable against the cosmic background. The evaporation time for such a giant is far longer than the current age of the universe. But for a primordial black hole with a very small mass, the story is dramatically different. A black hole with the mass of a small mountain would have a size smaller than a proton, but its evaporation would be a spectacular event. As it loses mass through Hawking radiation, the process accelerates. The smaller it gets, the hotter it becomes, and the faster it radiates energy. In the final, frantic seconds of its life, such a black hole would not fade away quietly. It would end its existence in a tremendous final burst of radiation, a flash that would peak in the gamma-ray part of the spectrum. It would be like a miniature bomb going off in space, a pinpoint detonation of high-energy light. Now consider the implications across cosmic history. If the early universe produced a vast number of these tiny primordial black holes, and if they have been steadily evaporating over the past 13.8 billion years, then the final moments of their lives would be happening all the time, scattered randomly throughout the cosmos. Could the combined gamma-ray flash from all these dying black holes be contributing to the diffuse background we observe? This idea transforms the gamma-ray background from an astrophysical puzzle into a potential laboratory for quantum gravity. The exact spectrum of radiation emitted in a black hole's final burst is a unique fingerprint predicted by Hawking's theory. If even a small fraction of the background had the specific energy signature of evaporating black holes, it would be a monumental discovery. It would not only confirm the existence of Hawking radiation, a phenomenon that has never been directly observed, but it would also provide irrefutable evidence for primordial black holes themselves. This would, in turn, solve another major mystery, the nature of dark matter. If a significant portion of the universe's missing mass is locked up in these ancient, small black holes, it would offer a compelling alternative to particle-based explanations like WIMP. However, the current data from telescopes like Fermi places severe constraints on this thrilling possibility. Scientists have meticulously searched the gamma-ray background and the sky in general for the telltale signs of these miniature explosions. They have looked for unexplained, short-duration gamma-ray flashes that could be the death throes of nearby primordial black holes. So far, none have been definitively identified. Furthermore, the smooth, steady nature of the background glow doesn't quite match what we might expect from a population of random, point-like explosions. If these events were a major contributor, the background might appear more granular or grainy than it actually is. The absence of a clear signal has allowed astronomers to effectively rule out primordial black holes over a wide range of masses as a dominant component of dark matter or as a primary source of the gamma-ray background. But the hunt is not over. Very small black holes that evaporated early in the universe's history would have left no trace for us to see today. And there remains a window for larger primordial black holes that are only now beginning to evaporate, whose Hawking radiation would still be too faint to detect. The search continues, a testament to how the faintest light in the cosmos can be used to test some of the most profound ideas about the nature of reality, from the quantum vacuum to the first instance of time. While the steady glow of galaxies and the persistent rumble of blazars provide a constant baseline, the universe is also punctuated by moments of sudden, extreme violence. This leads us to a mystery tied to specific cataclysmic encounters, the role of tidal disruption events. Imagine a star similar to our own Sun, going about its orderly orbit around the center of its galaxy. Its journey takes it dangerously close to the supermassive black hole lurking there. As the star approaches, the gravitational pull on the side facing the black hole becomes immensely stronger than the pull on the far side. This difference in force, known as a tidal force, stretches the star horribly, pulling it apart into a long, thin stream of gas in a process aptly named spaghettification. About half of this stellar debris is then flung away into the darkness, while the other half falls back onto the black hole, forming a hot, swirling accretion disk. The infall of material heats this disk to temperatures of millions of degrees, triggering a brilliant flare of radiation that can outshine the galaxy's billions of stars combined. This is a tidal disruption event, a cosmic feeding frenzy that signals the destruction of a star. For a long time, astronomers observed these events primarily in ultraviolet and optical light. However, more recent observations have revealed that under the right conditions, a tidal disruption event can also become a powerful source of gamma rays. This happens when the infalling material powers the launch of relativistic jets, similar to those seen in blazars but in a temporary, explosive outburst. If one of these jets is pointed in our direction, we detect a brilliant flash of high-energy gamma rays. Even without a jet, the intense radiation and particle acceleration in the accretion disk and the resulting shock waves can produce a significant amount of gamma ray emission. Each event is a transient spectacle, a brilliant flash that flares up and then fades over weeks or months. The fascinating question for the gamma ray background is one of statistics and persistence. While a single tidal disruption event is fleeting, the universe is both vast and ancient. In a cosmos filled with trillions of galaxies, each harboring a central supermassive black hole, these stellar demolitions are happening all the time. Current estimates suggest that in a typical galaxy, a star is torn apart by its central black hole roughly once every 10,000 to 100,000 years. That might sound infrequent, but when you multiply that rate by the staggering number of galaxies in the observable universe, it means that somewhere a star is being ripped apart almost constantly. At any given moment, there are thousands of these events occurring at various stages of their flare and decay across the cosmos. This leads to a compelling possibility. The combined, faded afterglow of all these distant, unresolved tidal disruption events could be contributing a faint, steady component to the isotropic gamma ray background. It would be akin to the faint, collective hum of a distant city heard from far away. You cannot distinguish any individual conversation or car horn, but the merged sound creates a persistent noise. Similarly, the gamma-ray photons from the peak and the decaying tail of countless tidal disruption events happening at different distances and times would arrive at Earth blended together into a smooth, diffuse glow. This signal would be particularly significant because it represents a direct tracer of black hole activity. Unlike the steady emission from an active galactic nucleus, which requires a persistent fuel supply, a tidal disruption event is a direct measurement of a black hole's mass and its immediate environment. The rate of these events tells us how often stars are being consumed, which in turn provides crucial information about the population of black holes in the universe, especially those that are dormant and not actively accreting material. If the gamma-ray background contains a measurable fraction from tidal disruption events, it would act as a unique cosmic census, counting the number of these monstrous gravitational pits and recording their feeding habits throughout cosmic history. Detecting this specific signature is incredibly challenging, as it requires disentangling it from the other, brighter contributors. But the potential reward is a new way to understand the life cycle of supermassive black holes and the dramatic fate of stars that venture too close. So far, we have been thinking about the gamma-ray background as a perfectly smooth, uniform fog. But what if we look closer? What if, on very fine angular scales, this seemingly featureless glow actually contains a subtle pattern of variations, a whisper of hidden structure? This brings us to a more sophisticated way of listening to the cosmos, moving beyond simply measuring the volume of the scream to analyzing its intricate texture. The key to this deeper listening is a powerful statistical tool called the Anisotropy angular power spectrum. Think of it like this. If you were standing in a dense, foggy forest and heard a constant, indistinct hum of insect noises, you might not be able to pick out a single cricket. But if you listened very carefully, you might notice that the sound isn't perfectly uniform. In one direction, the hum is slightly louder. In another, it has a slightly different pitch. By meticulously mapping these tiny variations in loudness, you could start to deduce things about the hidden population of insects, whether they are clustered in groups or spread evenly, and perhaps even estimate their typical distances from you. The anisotropy power spectrum does exactly this for the gamma-ray sky. Instead of just measuring the total intensity of the glow, astronomers measure how much that intensity fluctuates from one tiny patch of sky to the next. They break the sky down into a grid of incredibly small pixels and measure the minute differences in gamma-ray counts between them. The power spectrum then quantifies the strength of these fluctuations at different angular scales. Are the variations strongest on the scale of a full degree, or are they more prominent on scales as small as a few arc minutes? This pattern of clumpiness is a treasure trove of information. These small-scale anisotropies are not random noise. They are a direct fingerprint of the unresolved sources that make up the background. Each type of source leaves a distinct statistical signature. For example, consider blazars. We know that galaxies, and therefore the supermassive black holes at their centers, are not scattered randomly through space. They are clustered together by gravity, forming that immense cosmic web of filaments and voids. If blazars are a major contributor to the background, then the unresolved ones should reflect this large-scale structure of the universe. Their gamma-ray light should exhibit a specific pattern of clustering. It should be slightly brighter in directions that correspond to the dense nodes of the cosmic web and fainter in the voids. The power spectrum would show a particular signal, a certain amount of power, on angular scales that match the typical distance between these clusters of galaxies. Now contrast this with another candidate, star-forming galaxies. While these galaxies are also clustered, their distribution is different from that of the rare, extremely bright blazars. There are far more ordinary star-forming galaxies, and they are spread throughout the cosmic web in a different way. Their unresolved emission would create a different pattern in the anisotropy map. The fluctuations would likely be smoother or have a different characteristic scale. Furthermore, there is a third crucial component, the emission from within our own Milky Way galaxy. Cosmic rays interacting with interstellar gas produce a diffuse gamma-ray glow that is brightest along the galactic plane and fainter at the poles. This foreground emission has its own, very strong anisotropic signature that astronomers must carefully subtract from the data to see the truly extragalactic signal. The process is like trying to hear a faint, distant choir while standing next to a roaring waterfall. You first have to find a way to filter out the sound of the water. The incredible promise of the anisotropy power spectrum is its ability to act as a cosmic fingerprinting tool. By comparing the measured pattern of fluctuations to predictions from different theoretical models, one where blazars dominate, another where star-forming galaxies are the main source, and so on, scientists can determine which mix of populations best matches the real data. It is a powerful statistical test that doesn't require us to see any single source directly. The Fermi Gamma-Ray Space Telescope has been collecting the immense dataset needed for this analysis for over a decade. The latest results are revealing and complex. The fluctuations observed are indeed significantly larger than what we would expect if the background were purely smooth, confirming that it is indeed composed of a vast number of point sources too faint to see individually. More intriguingly, the data shows that no single population of sources can explain the observed power spectrum. The pattern of clumpiness suggests a blend. It points toward a scenario where the unresolved emission from blazars is responsible for the fluctuations on larger angular scales, tracing the cosmic web, while the emission from many more numerous but less clustered star-forming galaxies contributes more to the fluctuations on smaller scales. This multi-component explanation is fitting the data better than any single source model, moving us closer to a complete inventory of the gamma-ray sky. By listening not just to the volume of the cosmic scream, but to its subtle texture, we are beginning to count and categorize the invisible monsters and factories that fill the void. While we search for clues in the distant universe, some of the most startling evidence might be emanating from our own cosmic backyard, pointing toward a phenomenon that could be happening in galaxies across the cosmos. This brings us to the enigmatic structures known as the Fermi bubbles, discovered just over a decade ago by the very telescope that bears their name. These are colossal, hourglass-shaped lobes of gamma-ray emission erupting from the center of our Milky Way, extending an astonishing 25,000 light-years above and below the galactic plane. To grasp their scale, if our eyes could see gamma rays, these bubbles would dominate the night sky, covering a region as large as 50 full moons. They are a clear testament to a past cataclysm, a sign that the supermassive black hole at the heart of our galaxy, named Sagittarius a star, was not always the quiet, passive object it is today. Sometime within the last few million years, it must have experienced a period of intense activity, gorging on surrounding material and unleashing a titanic, bipolar outburst of energy and particles that inflated these massive cavities in the hot gas halo that surrounds the Milky Way. The existence of these bubbles immediately suggests a profound and universal possibility. If our own relatively quiet galaxy experienced such an energetic outburst, then it is almost a certainty that other galaxies have too. In fact, for galaxies with actively feeding supermassive black holes, these events might be a regular part of their life cycle. We should expect to find similar, or even far larger, gamma-ray bubbles surrounding active galaxies throughout the universe. And this leads directly to a compelling question about the gamma-ray background. Could the combined, unresolved light from the Fermi bubble-like structures around countless distant galaxies be a significant contributor to the isotropic signal we observe? Imagine each galaxy surrounded by a faint, extended halo of gamma-ray emission, a ghostly imprint of its most recent black hole eruption. From our vantage point billions of light-years away, we would not be able to resolve these individual bubbles around any single galaxy. Their faint, diffuse light would instead blend together into a smooth, all-sky glow, seamlessly adding to the background hum. Testing this idea requires a careful analysis of what such emission would look like. The gamma rays from these bubbles are not produced in the same way as those from a blazar's jet. Instead, they are thought to be generated by a process known as inverse Compton scattering. The outburst from the black hole would have filled the bubbles with ultra-high-energy electrons. As these electrons travel through the bubbles, they collide with low-energy photons that fill space, such as the ancient light of the cosmic microwave background or the collective starlight from the galaxy. In these collisions, the electrons transfer a tremendous amount of energy to the photons, boosting them from their low-energy state all the way up into the gamma-ray regime. The resulting emission is diffuse and spread across the entire volume of the bubble, creating a vast, extended source of high-energy light. The key to estimating their contribution to the background lies in their longevity. A brilliant blazar flare might last for days or years, but the gamma-ray bubbles around a galaxy are thought to persist for millions of years after the initial black hole outburst has subsided. They are the long-lasting afterglow of a past eruption. This means that at any given moment in cosmic history, a large fraction of all galaxies could be surrounded by these fading structures. When we look out into the universe, we are seeing snapshots of galaxies at different stages of their evolution. Some will have young, bright bubbles from a recent eruption, while others will have older, fainter ones. The combined glow from this cosmic population of bubbles would be remarkably smooth and isotropic, just like the background we measure. Calculating the exact intensity of this cumulative glow is a complex task for astrophysicists. It depends on factors like how often a typical galaxy's black hole has an outburst, how much energy is injected into the bubbles, and how quickly the gamma-ray emission fades over time. If these outbursts are common and energetic, the collective emission could be a substantial component of the background, particularly at certain energy ranges. If they are rarer or weaker, their role would be more minor. The hunt is on to find direct evidence of these extragalactic bubbles. With more sensitive future telescopes, astronomers hope to resolve these faint structures around nearby galaxies, providing the crucial data needed to weigh their importance. The existence of our own Fermi bubbles serves as a powerful reminder that the universe is not in a steady state. It is punctuated by violent, transformative events, and the echoes of those events, both near and far, may be written in the faint gamma-ray light that bathes us all. Now we come to a source of gamma rays that exists not within the bright disks of galaxies, but in the immense, dark spaces that surround them. Every galaxy, including our own Milky Way, is cocooned within a massive, invisible atmosphere of incredibly hot, diffuse gas. This is the circumgalactic medium, a halo of matter that can extend for hundreds of thousands of light years, far beyond the visible edge of the galaxy's stars. This gas is not dormant, it is the site of a continuous, sprawling exchange. It acts as a reservoir, absorbing material blown out by stellar winds and supernova explosions, and also as a source, feeding fresh gas back into the galaxy to fuel future generations of stars. It is within this vast, dynamic halo that a subtle but potentially significant process for generating gamma rays may be taking place on a truly colossal scale. The story begins with the cosmic rays that are constantly being manufactured inside the galaxy. As we've discussed, particles are accelerated to nearly the speed of light by supernova shocks and other violent events. While many of these cosmic rays remain trapped by the galaxy's magnetic fields, a substantial fraction of them must eventually escape, leaking out into the circumgalactic medium. Once they break free from the confines of the galactic disk, they enter a realm of incredibly thin but pervasive gas. This is where a secondary production mechanism kicks in. These escaped cosmic rays, predominantly high-energy protons, then travel through the circumgalactic gas for millions of years. During their long journey, they inevitably collide with the protons and atomic nuclei that make up this tenuous atmosphere. These are the same proton-proton collisions that produce gamma rays inside galaxies, but here they are happening over an immensely larger volume. The key difference is one of density and scale. Inside a galaxy, the gas is dense, so collisions are frequent and the gamma-ray emission is relatively bright but concentrated. In the circumgalactic medium, the gas is millions of times thinner, so the rate of collisions is correspondingly much lower. However, the volume of space involved is astronomically larger. The collective glow from these countless, infrequent interactions across such a vast expanse could add up to a substantial and, crucially, perfectly diffuse source of gamma-ray light. This presents a monumental challenge for astrophysicists trying to model its contribution. The process depends on factors that are incredibly difficult to measure. First, we need to know exactly how much cosmic ray energy is able to escape from a typical galaxy. This is not a fixed number. It depends on the strength and configuration of the galaxy's magnetic fields and the intensity of its star-forming activity. A more active galaxy with more supernova will inject more cosmic rays into its halo. Second, we need a precise map of the density and temperature of the circumgalactic gas itself. This gas is so hot and thin that it is virtually invisible in most wavelengths of light, and we can only study it indirectly by observing how it absorbs the light from distant quasars shining through it. Building a realistic three-dimensional model of this halo is an ongoing effort in modern astronomy. If the circumgalactic medium is even slightly denser or more extensive than our current best estimates, the gamma-ray output from these interactions could be significantly higher. The profound implication of this process is that it would produce a component of the gamma-ray background that is fundamentally different from the unresolved light of point sources like blazars or distant galaxies. This would be a truly diffuse emission. It doesn't come from objects that are too far away to see. It originates from the empty-looking space around those objects. This makes it exceptionally difficult to distinguish, as it would smoothly blend with the other diffuse signals. However, it might have a unique spectral signature, a specific pattern across different gamma-ray energies that reflects the particular conditions in these hot halos. Detecting this signature would do more than just add another piece to the gamma-ray puzzle. It would provide a revolutionary new way to study the circumgalactic medium itself. We could use gamma rays as a probe to weigh these massive gas halos and understand the grand cycle of matter flowing into and out of galaxies, witnessing the lifeblood of galactic evolution on the largest scales. But what about the smaller, more frequent explosions that light up our cosmic neighborhood? This leads us to a quieter, yet incredibly numerous class of events, classical nova. Unlike the supernova that mark the complete destruction of a star, a nova is a surface-level cataclysm. It occurs in a binary star system where a white dwarf, the dense, Earth-sized core of a sun-like star that has run out of fuel, is locked in a gravitational dance with a companion star. The white dwarf's intense gravity steadily pulls hydrogen-rich gas from its neighbor. This stolen material accumulates on the white dwarf's surface, building up pressure and heat until it reaches a critical threshold. Then, in a spectacular, runaway thermonuclear explosion, the entire hydrogen layer ignites like a bomb. The star can suddenly increase in brightness by a factor of 50,000 or more, blazing forth for days or weeks before gradually fading. For a long time, astronomers observed these beautiful, recurring flares in visible light, considering them important but relatively local phenomena. The perspective on nova changed dramatically with the launch of the Fermi Gamma-Ray Space Telescope. To the astonishment of many, Fermi began detecting high-energy gamma rays coming from these events. This was entirely unexpected. The conventional wisdom was that the energies involved in a nova explosion were too low to produce radiation of such high frequency. The discovery revealed that nova are far more potent particle accelerators than anyone had guessed. The leading theory suggests that the initial thermonuclear blast creates a powerful shock wave that plows through the expanding shell of ejected material. This shock acts as a natural particle accelerator, boosting protons to near-light speeds. When these relativistic protons collide with other nuclei in the ejected gas, they generate gamma rays, specifically through the decay of neutral pions, the same process that occurs in supernova remnants and galaxy clusters. So, while a nova is certainly not as powerful as a gamma ray burst or a flaring blazar, it is now confirmed as a genuine, albeit modest, source of gamma-ray photons. This discovery immediately raises a fascinating question for the cosmic background. A single nova is a faint speck in the gamma-ray sky, even when it happens in our own galaxy. But their defining characteristic is their sheer frequency. In our Milky Way alone, astronomers estimate that between 20 and 50 nova occur every single year. Many are hidden from our view by dense clouds of interstellar dust, but they are happening constantly. Now, expand that number to encompass the trillions of galaxies in the observable universe. The rate becomes staggering, with nova erupting somewhere in the cosmos at a rate of thousands per second. Each one produces a brief, faint pulse of gamma-ray light. Individually, these pulses are completely undetectable from intergalactic distances. But what about their collective cumulative effect? Could the combined light from all the nova that have ever exploded, their faint signals overlapping across space and time, create a faint, steady component of the isotropic gamma-ray background? It would be the ultimate example of the power of numbers, the gentle, persistent rain of countless tiny events blending into a discernible hum. Calculating this potential contribution is a complex exercise in cosmic statistics. Astrophysicists take the gamma-ray luminosity measured from the handful of nearby nova that Fermi has been able to observe. They then use our understanding of stellar populations and star formation history to estimate how many nova occur in a typical galaxy per year. This rate is then multiplied by the total number of galaxies across cosmic history, factoring in that the nova rate was likely higher in the past when stars were forming more rapidly. The initial results of these calculations suggest that while nova are unlikely to be the dominant source of the background, their integrated light could be measurable. They might contribute a few percent to the total diffuse glow, particularly at the lower end of the gamma-ray energy spectrum. This may sound like a small amount, but in the precise science of background modeling, every percent matters. Accounting for this component is crucial for accurately isolating the signal from other, more exotic sources like dark matter. The implications of this possibility extend beyond just filling in a small piece of the puzzle. If nova do contribute to the background, it means that this faint glow is truly a composite of cosmic violence on all scales, from the unimaginable power of supermassive black holes to the comparatively humble eruptions of dying stellar embers. Furthermore, it provides a unique way to study the nova phenomenon itself on a universal scale. By constraining their total contribution, we can check our models of how often they occur and how efficiently they accelerate particles. Any discrepancy between the predicted nova background and the actual measured background could indicate that our understanding of these common explosions is incomplete. Perhaps they are more efficient gamma-ray producers under certain conditions, or maybe their occurrence rate in different types of galaxies is not what we expect. The diffuse gamma-ray background, therefore, becomes a tool for taking a census of these stellar events across the entire universe, allowing us to understand the life and death of common star systems in a way that would be impossible by studying only the rare, nearby examples we can see in detail. The search for answers to the gamma-ray background's mysteries often leads us to question the very nature of the particles themselves and the rules that govern their journey across the cosmos. This brings us to a hypothesis that is as elegant as it is revolutionary, a concept that suggests the photons we detect may have undergone a strange transformation along the way. The idea centers on hypothetical particles known as action-like particles, or ALP, originally proposed to solve a deep problem in particle physics concerning the strong nuclear force. ALPs are theorized to be incredibly light, chargeless particles that interact only very weakly with normal matter. But their most fascinating property in the context of gamma rays is their potential relationship with light. In the presence of a magnetic field, a gamma-ray photon could, in theory, transform into an ALP. This process is akin to a magical act of disguise. The high-energy photon momentarily ceases to be light and becomes something else entirely, a ghostly particle that can slip through the universe almost completely unimpeded. This ability to switch identities has profound implications for how we interpret the gamma-ray background. One of the major obstacles for high-energy gamma rays traveling great distances is their interaction with the extragalactic background light, the fog of starlight that fills the universe. As we discussed, this EBL absorbs gamma rays, especially those at the highest energies, creating an absorption horizon that limits our view. But if a gamma ray can temporarily convert into an ALP when it encounters a region of intense magnetic field, such as those found within a galaxy cluster or along the filamentary structures of the cosmic web, it becomes invisible to this fog. While in its ALP form, the particle does not interact with the starlight photons, it simply passes through them. Then, later in its journey, when it encounters another magnetic field, it can convert back into a gamma-ray photon, once again becoming detectable. This oscillation between photon and ALP states effectively gives the gamma-ray a means of teleporting through the cosmic fog. It can travel much greater distances than standard physics would allow, meaning we could be seeing gamma-ray sources that are actually far more distant than our models suggest. This process would leave a very specific and detectable imprint on the gamma-ray background. First, it would alter the observed energy spectrum. The characteristic absorption dip caused by the EBL would appear smoothed out or less pronounced than expected. The universe would seem more transparent to high-energy gamma rays than it has any right to be. Second, and perhaps more intriguingly, it would affect the anisotropy, the pattern of fluctuations in the background. Because the conversion probability depends on the strength and configuration of magnetic fields, the background would not be perfectly smooth. Instead, we might expect to see subtle correlations between the gamma-ray glow and the large-scale structures of the universe where these magnetic fields are known to exist. It would be as if the cosmic web, traced by galaxies and galaxy clusters, is casting a faint magnetic shadow onto the gamma-ray sky. Finding such a correlation would be incredibly strong, albeit indirect, evidence for the existence of ALPs. The hunt for this signature is a direct probe of physics beyond the standard model. Confirming that gamma rays oscillate into ALPs would not only solve an astrophysical puzzle, but would also unveil an entirely new component of the universe, a previously hidden sector of ultralight particles. This discovery would have ramifications far beyond gamma-ray astronomy, impacting our understanding of dark matter and fundamental symmetries in nature. Telescopes like Fermi are therefore acting as immense particle physics detectors, using the entire universe as their laboratory. By meticulously analyzing the subtle distortions in the gamma-ray background spectrum and its fluctuations, scientists are conducting a sensitive test for the existence of these elusive particles. It is a testament to how the most persistent cosmic mysteries often push us to consider the most fundamental possibilities, where the solution requires not just a new telescope, but a new law of physics. To push our investigation even further back in time, we must consider the very origins of the cosmic structures we see today. This leads us to a mystery that connects the gamma-ray background to the universe's first dawn of light, a pivotal chapter known as the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was a profoundly dark and simple place. It was filled with a thick, pervasive fog of neutral hydrogen gas through which light could not travel freely. The universe was in a cosmic dark age. Then, something revolutionary happened. The first stars and galaxies began to flicker into existence. These were not the familiar, well-behaved stars of today. The first stars, often called population 3 stars, were behemoths, hundreds of times more massive than our Sun. They lived fast and died violent deaths, burning through their nuclear fuel in only a few million years before exploding as supernova or collapsing directly into black holes. The intense ultraviolet radiation from these first stars and the accretion disks of the first black holes began to rip electrons away from the surrounding neutral hydrogen atoms, a process known as ionization. Slowly, like countless tiny fires burning away a global fog, these first sources of light created ever-expanding bubbles of ionized transparent gas. Over several 100 million years, these bubbles overlapped and merged until the entire universe had been reionized, transforming it from an opaque fog into the clear, transparent space we observe today. The question for gamma-ray astronomy is whether this foundational era left any detectable mark on the high-energy background we see now. Could the violent deaths of those first monstrous stars have produced a sufficient amount of gamma-ray radiation to leave a faint, fossilized imprint? The mechanisms are certainly plausible. A population 3 star ending its life in a supernova would have been an event of almost unimaginable power, far exceeding the explosions we see in the modern universe. The shock waves from such a detonation would have been tremendous particle accelerators, generating cosmic rays that, upon collision, would produce gamma rays. Furthermore, the first black holes, feasting on the pristine gas of the early universe, could have generated powerful, short-lived jets. even if these individual events are far too distant and faint for any telescope to ever see directly, their combined output across the entire epoch of reionization might have contributed a unique component to the diffuse background. This would be the most ancient signal conceivable, a whisper from the time when the universe was lighting its first candles. Detecting such an imprint, however, is a challenge of extraordinary difficulty. A primary obstacle is that any gamma-ray photons produced during reionization have been traveling for over 13 billion years to reach us. During that immense journey, they have been stretched by the expansion of the universe, their wavelengths lengthened by a factor of 10 or more. This cosmological redshift means that a gamma-ray photon emitted in the early universe would arrive at Earth with its energy significantly reduced, possibly shifted down into the X-ray or even ultraviolet part of the spectrum. The direct gamma-ray light from the reionization era may not even be in the gamma-ray band anymore by the time it gets to us. Therefore, the signature we would be looking for is not a bright flash, but an extremely subtle distortion in the very lowest energy end of the gamma-ray background spectrum. It would be an excess of photons that cannot be accounted for by any nearby or more recent sources. The scientific value of finding even a hint of this signal would be incalculable. It would provide a completely new and direct window into an era that is currently studied through indirect means, primarily by observing the absorption lines in the light of the most distant quasars. A gamma-ray fossil would tell us not just about the light from the first objects, but about their high-energy violence. It would give us crucial information about the nature of those first stars and black holes, how massive they were, how often they exploded, and how efficiently they could accelerate particles. This would help resolve major debates in cosmology, such as whether stars or black holes were the primary drivers of reionization. The gamma-ray background in this context becomes a potential palimpsest, a document on which the universe's first chapter was written in high-energy light, and though it has been faded and overwritten by billions of years of subsequent history, a few faint strokes from that original text might still be visible to the most careful and ingenious observers. Even after more than a decade of meticulous observation, one of the most humbling facts for gamma-ray astronomers is the sheer number of sources that remain stubbornly anonymous. The Fermi telescope's catalog is filled with objects that definitively emit gamma rays, yet whose true nature is a complete mystery. These are not faint, theoretical specks. They are bright enough to be detected and catalogued, but they defy classification. They do not neatly match the signature of a known blazar, a pulsar, or a supernova remnant. This vast population of unidentified sources represents a known unknown, a glaring gap in our map of the high-energy sky. The critical question is whether this hidden menagerie contains a new, numerous class of faint gamma-ray emitters whose collective light is seamlessly blended into the diffuse background we measure. Imagine if we have been trying to identify the instruments in an orchestra by listening only to the loudest soloists, while a whole section of quieter, unfamiliar instruments has been playing all along, their individual voices too soft to pick out, but their combined sound essential to the overall harmony. These unidentified sources could be that missing section, a population of objects so common and widespread that their unresolved emission forms a fundamental component of the cosmic glow. The potential for discovery here is immense. What could these objects be? They might be known astrophysical objects behaving in unexpected ways. Perhaps they are a unique type of pulsar with an unusual beam pattern or a spin rate that makes their gamma-ray pulses difficult to identify in our data. They could be binary star systems where the interaction between a compact object and a normal star produces gamma rays through processes we haven't yet modeled accurately. Or they could be something entirely novel, a class of celestial engine that has simply never been theorized because we've never had an instrument like Fermi to reveal its existence. The key characteristic that makes them so relevant to the background mystery is their abundance. If these unidentified sources are indeed a distinct population, and if they are as numerous as the catalogue suggests, then their combined output could be substantial. When we add up the light from all the blazars and star-forming galaxies we can identify, we are still left with a deficit. It is perfectly plausible that this missing energy is coming from these very sources, a population we can see but cannot yet name, whose individual identities are hidden in plain sight. This leads directly to a powerful and evolving method of investigation, time-domain astronomy. The universe is not a static photograph, it is a dynamic movie, and many of its most fascinating characters reveal themselves through change. Up until now, our discussion of the background has largely treated it as a steady, constant signal. But what if a significant portion of that signal is actually the time-averaged glow from countless transient event sources that flare up brightly and then fade away? The Fermi telescope is uniquely suited to explore this possibility because it continuously monitors the entire sky every few hours. This allows it to catch the rise and fall of gamma-ray sources over time. We already know about spectacular transients like gamma-ray bursts and some tidal disruption events, but there could be a whole zoo of less dramatic, more frequent variables that have so far escaped our notice. Consider the possibility of a large population of objects that spend most of their time in a quiet, low-emission state, but experience regular, brief outbursts. During these flares, they become bright enough for Fermi to detect, earning them a spot in the catalogue as an unidentified source. But once the flare subsides, they fade back into obscurity, leaving astronomers with a single data point and no clear counterpart in other wavelengths to confirm their identity. If such flaring objects are common throughout the universe, then at any given moment, a certain percentage of them will be in an active state, contributing their flickering light to the overall sky. When we take a long exposure picture of the cosmos, which is essentially what the gamma-ray background is, the light from all these individual flares averages out into a steady, diffuse glow. The background in this scenario isn't just made of faint, steady sources. It's also the cinematic blur of countless cosmic fireflies, each flashing too briefly to be seen individually, but together creating a persistent light. Future studies focused on this time-domain aspect are poised to revolutionize our understanding. By applying sophisticated statistical tools to Fermi's immense dataset, astronomers can search for subtle correlations and patterns in the variability of the unidentified sources. They can look for objects that flare with a specific periodicity, hinting at an orbital motion in a binary system, or for sources that have a characteristic rise and fall time, similar to a known class of variable star. The next generation of telescopes operating across the electromagnetic spectrum from radio to optical to X-rays will be crucial for this follow-up work. When Fermi detects a flare from an unknown source, alerting a network of other observatories to quickly swing into action could provide the crucial multi-wavelength data needed to crack the case. Identifying even a small fraction of these mysterious sources could unlock the door to understanding the rest. If we discover that a group of them are, for example, a previously unknown type of magnetic cataclysmic variable star, we can then estimate how common such stars are in the universe and calculate their total contribution to the background. The hunt for the identity of these unknown sources is therefore not a separate puzzle from the mystery of the diffuse glow. It is likely the very key to solving it, reminding us that sometimes the most important secrets are not hidden in the dark, but are camouflaged among the points of light we have already found. We have been thinking of the journey of a gamma-ray photon as a simple, straight-line path from its source to our telescopes. But for the very highest energy photons, the voyage can be far more complex and transformative, a cascade of creation that turns a single particle of light into a shower of secondary particles. This bizarre process, known as an electromagnetic cascade, might seem like an obscure detail of particle physics, but it holds the key to probing one of the most elusive features of the cosmos, the magnetic fields that permeate the seemingly empty space between galaxies. The cascade begins with a single ultra-high-energy gamma-ray photon embarking on an intergalactic journey. After traveling some distance, it encounters a photon from the extragalactic background light, the ancient sea of starlight. This is no gentle meeting, it is a collision with enough energy to spawn matter. The gamma-ray photon vanishes, and in its place, an electron and its antimatter counterpart, a positron, are conjured into existence. This is the famous equation E equals mc squared in action, energy transforming directly into mass. But the story does not end there. These newborn electrons and positrons are now traveling at almost the speed of light, and they are immediately immersed in another pervasive energy field, the cosmic microwave background radiation, the leftover heat from the Big Bang. As these high-speed charged particles plow through this radiation bath, they experience a violent deceleration. This causes them to lose energy by emitting new gamma-ray photons, a process called inverse Compton scattering. These secondary gamma rays then have enough energy to repeat the entire cycle, colliding with more starlight photons to create more electron-positron pairs, which in turn generate even more gamma rays. A single ultra-high-energy photon can thus initiate a chain reaction, a broad cascade of particles and light that fans out as it travels through space. This is where the intergalactic magnetic field enters the picture. Until now, we have largely considered the voids between galaxies to be true vacuums, devoid of any significant structure. But we know that space is not entirely empty. It is threaded with incredibly weak magnetic fields. These fields are thought to be relics from the early universe, amplified over time by the motion of plasma during the formation of the cosmic web. They are unimaginably faint, billions of times weaker than the magnetic field of a common refrigerator magnet. Detecting them directly has been considered nearly impossible. However, they have a crucial effect on the electromagnetic cascade. The newly created electrons and positrons are charged particles, and charged particles are deflected by magnetic fields. As the cascade develops, the paths of these electrons and positrons are bent and twisted by these weak fields. This bending changes the entire geometry of the cascade. Instead of a relatively narrow beam of secondary gamma rays continuing in the original direction of the primary photon, the cascade becomes broadened and smeared out. The secondary gamma rays are emitted from these deflected particles, meaning they arrive at Earth from slightly different directions. This subtle effect provides us with a brilliant, indirect way to measure the invisible. The gamma-ray background, particularly at the highest energies, is not just a collection of point sources. It is also the accumulated light from these cascades that have been initiated by the most energetic particles in the universe. By studying the angular spread or the diffuseness of this highest energy component, astronomers can work backwards to infer the properties of the magnetic fields that shape the cascades. If the gamma-ray sky at these energies appears smoother and more spread out than our models predict, it is a strong indication that intergalactic magnetic fields are present and are acting to deflect the cascade particles. The degree of this smoothing tells us about the field's strength, while patterns in the smoothing could even hint at its structure, whether it is tangled like a ball of yarn or organized into larger-scale filaments. Using the cosmos as a giant particle physics detector in this way is a frontier of modern astronomy. It transforms the gamma-ray background from a puzzle to be solved into a precision instrument for exploration. A confirmed detection of these fields would be a monumental discovery. It would reveal that the great voids are not featureless deserts, but are imprinted with a faint fossil record of the universe's turbulent youth, a subtle magnetic tapestry woven into the fabric of space itself. This would have profound implications for our understanding of how the cosmic web formed and how energy is transported across the largest scales of the universe. The faintest glow in the sky, when decoded with the right physical principles, can illuminate the darkest and most expansive regions of the cosmos. shifting our focus from the vast intergalactic voids to the turbulent hearts of galaxies themselves. We arrive at a mystery that ties one of astronomy's oldest puzzles directly to the gamma-ray sky, the origin of cosmic rays. For over a century, we have known that Earth is constantly bombarded by a rain of high-energy atomic nuclei, primarily protons, traveling at nearly the speed of light. But where do these cosmic bullets come from? The leading theory points to a specific, violent engine common throughout the universe, the supernova remnant. When a massive star explodes, it does not simply vanish. It unleashes a shock wave that expands outward at tens of thousands of kilometers per second, plowing into the surrounding interstellar medium. This shock front is a perfect natural particle accelerator. As charged particles encounter the shock, they can be trapped, bouncing back and forth across its boundary. With each crossing, the magnetic fields embedded in the shock transfer a little more energy to them, gradually boosting them to the phenomenal velocities we observe. It's an incredibly efficient process, and the sheer power of a supernova explosion provides more than enough energy to account for the cosmic rays we detect. The crucial link to gamma rays lies in what happens next. These newly minted cosmic rays, now traveling at relativistic speeds, do not remain confined to the remnant forever. They escape and diffuse throughout the galaxy, but a significant fraction of them interact with the dense material of the remnant itself or the surrounding gas clouds. When a high-energy cosmic ray proton smashes into a slower-moving proton from the interstellar gas, their collision can create a short-lived particle called a neutral pion. This pion then decays almost instantly into two gamma-ray photons. This process transforms the kinetic energy of the explosion, funneled through cosmic ray acceleration, directly into high-energy light. In our own galaxy, telescopes like Fermi have beautifully confirmed this theory by detecting extended shells of gamma-ray emission surrounding known supernova remnants. The gamma-ray glow neatly traces the location of the shock wave, providing a direct visual map of where particle acceleration is occurring. It's a confirmed physical mechanism operating right here in our cosmic backyard. Now extend this idea to its ultimate, universal conclusion. If supernova remnants are the primary particle accelerators in the Milky Way, then the same must be true for every star-forming galaxy in the cosmos. The life cycle of massive stars, their birth, brief lives, and explosive deaths is a fundamental process that repeats itself in galaxies across the universe. Each star-forming galaxy is therefore a factory for cosmic rays and, consequently, a source of gamma-ray light generated by those cosmic rays. The critical point is that we can only see the brightest, closest supernova remnants as individual objects. For a galaxy millions or billions of light-years away, the gamma-ray light from any single remnant within it is far too faint to resolve. Instead, what we would detect is the combined glow from every supernova remnant in that distant galaxy, all blending together into a single, faint point of gamma-ray light. And when we look at the entire sky, the light from all those distant galaxies, each one humming with the faint, collective gamma-ray emission of its own population of supernova remnants, would blend seamlessly into the smooth, isotropic background we observe. This makes the unresolved gamma-ray background a powerful test for one of astrophysics' core theories. If supernova remnants are indeed the dominant source of galactic cosmic rays, then their cumulative emission should form a significant foundational layer of the background. Calculating this expected contribution is a complex task that involves understanding the rate of supernova throughout cosmic history, the average efficiency of cosmic ray acceleration in a typical remnant, and how that gamma-ray emission evolves as a remnant expands and fades over thousands of years. The results of these models are fascinating. They suggest that this component could be substantial, potentially accounting for a major portion of the background glow at certain energies. However, it also highlights a potential tension. If the supernova remnant contribution is as large as some models predict, it might leave less room for other exotic explanations like dark matter. Alternatively, if the observed background is even brighter than the supernova remnant models can account for, it could indicate that our understanding of these celestial accelerators is incomplete. Perhaps supernova in the early universe, occurring in environments richer in gas and dust, were even more efficient at producing gamma rays than their modern counterparts. The gamma ray background in this context becomes a cosmic calibration tool. It allows us to check our local understanding of particle acceleration against the universal average, providing a way to see if the physics we observe in our neighborhood holds true across 13.8 billion years of cosmic evolution. While we have been captivated by the brilliant beacons of blazars, it is easy to overlook the fact that for every one of those dazzling monsters, there may be thousands of far quieter, more sedate relatives. This brings us to a population of objects that could be the true silent majority of the high-energy universe, low-luminosity active galactic nuclei. Imagine a supermassive black hole that is not in a frenzied feeding frenzy, but is instead on a strict cosmic diet, slowly sipping on a meager trickle of gas and dust. This is the realm of the low-luminosity AGN. Their central engines are still active, but they are operating at a fraction of their potential power, like a colossal jet engine idling on a runway rather than roaring at full throttle for takeoff. The challenge with these objects is that their faint, individual gamma-ray glow is incredibly difficult to detect, even with our most powerful telescopes. A blazar is a blinding searchlight pointed directly at us, but a low-luminosity AGN is a faint, distant candle, its light easily lost in the glare of its own galaxy. It is precisely their faintness, however, that makes them such compelling candidates for explaining the smooth, pervasive nature of the gamma-ray background. The logic is one of sheer demographics. In the cosmos, the rule is almost always that the fainter an object is, the more numerous it becomes. There are far more dwarf stars than giants, far more small galaxies than large ones. The same principle almost certainly applies to active black holes. The universe could be teeming with these low-luminosity engines, a vast population that has so far remained hidden below the detection threshold of our surveys. While each one contributes only a minuscule amount of gamma radiation, their collective output when summed across the entire observable universe could be immense. It is the ultimate example of strength in numbers, the quiet murmur of countless faint voices blending together into a roar that rivals the occasional brilliant shout. The physics powering these gentle giants is also fundamentally different from their brighter cousins. In a luminous AGN, material falls onto the black hole in a dense, chaotic accretion disk, heating up to incredible temperatures and powering those magnificent jets. In a low-luminosity system, the accretion process is thought to be far more orderly and inefficient. The infalling gas may form a much thinner, cooler disk, or it might accrete in a different mode altogether, such as an advection-dominated flow. In this scenario, instead of radiating away its energy as light, much of the heat is simply swallowed by the black hole along with the gas. This results in a much dimmer object across all wavelengths, including gamma rays. Furthermore, the jets produced by these systems are likely weaker, slower, or may not even be present in the same structured form. The gamma rays they produce might be generated through different mechanisms, perhaps in more diffuse lobes or through interactions closer to the black hole itself. This difference in internal physics could leave a unique fingerprint on the gamma ray background. If low luminosity AGN are a major component, they might impart a specific spectral shape to the diffuse glow, a particular distribution of gamma-ray energies that differs from the signature of powerful blazars or star-forming galaxies. Their emission might peak at lower energies or have a softer, smoother spectrum. Identifying this subtle signature is like trying to identify a specific instrument in a symphony by its tone alone, even when you cannot see the musician. It requires exquisitely precise measurements of the background spectrum and a deep theoretical understanding of how these different engines operate. The hunt for this signature is more than just an accounting exercise. It is a probe into the most common state of black hole activity in the universe. It forces us to ask what most supermassive black holes spend most of their time doing. The answer appears to be that they are not the brilliant monsters of legend, but are instead often quiet, modest consumers whose collective presence nonetheless paints the entire cosmos with a faint, high-energy brushstroke. But what if we've been thinking about dark matter in entirely the wrong way? For decades, the hunt has been dominated by the idea of WIMP, weakly interacting massive particles. This is a bottom-up approach where dark matter is composed of particles that were created in the hot, dense early universe and then clumped together over time to form the large-scale structures we see today. Their potential gamma-ray signal comes from these particles annihilating each other in a final flash of light. However, there exists a far more exotic and dramatic class of theories known as top-down models. In this radical scenario, dark matter isn't made of stable, fundamental particles waiting to annihilate. Instead, it could consist of primordial relics so massive and unstable that they have been decaying since the beginning of time, and it is this very process of decay that injects high-energy radiation, including gamma rays, into the cosmos. The candidates for this top-down dark matter are as fascinating as they are speculative. One possibility involves super-heavy particles with names like WIMP-zillas, particles so massive that their rest energy is equivalent to the entire energy of a nuclear explosion compressed into a single subatomic point. These behemoths would have been forged in the extreme conditions of the very early universe, perhaps during a period of rapid expansion known as inflation. Unlike WIMP, they would not annihilate. Their immense mass would make them effectively stable for billions of years, but not perfectly so. Over cosmic timescales, they could spontaneously decay, their tremendous mass energy converting directly into a shower of standard model particles, including a cascade of gamma rays. Another, even more abstract idea points to cosmic defects. As the universe cooled and underwent phase transitions after the Big Bang, similar to how water freezes into ice, imperfections could have been frozen into the fabric of spacetime itself. These defects might take the form of cosmic strings, incredibly thin, ultra-dense filaments of energy vibrating through the cosmos, or domain walls, vast two-dimensional sheets separating regions of space with different vacuum properties. The decay or annihilation of these topological defects would release fantastic amounts of energy, potentially appearing as a smooth, pervasive background of high-energy radiation. The crucial distinction for the gamma-ray background lies in the energy spectrum these top-down models predict. Annihilation processes, like those expected from WIMP, typically produce a gamma-ray spectrum that has a relatively soft cutoff, a gradual decline at the highest energies. In contrast, the decay of a super-heavy particle or the dissolution of a cosmic defect often generates a much harder spectrum. This means a greater proportion of the gamma rays are produced at the very highest energies. When astronomers look at the observed gamma ray background, they do see an excess of photons at these high energies, a bump that is difficult to explain with conventional astrophysical sources alone. This anomaly makes top-down models particularly enticing, as they naturally predict a signal that could better match this puzzling feature of the data. It's as if the universe is presenting us with a clue that points away from the gentle fade out of annihilation and toward the sharp, explosive finale of a decaying relic. However, the appeal of these models is tempered by severe constraints from other branches of physics and astronomy. If such powerful, decaying dark matter were flooding the universe with high-energy particles, it would have other observable consequences. For instance, the decay products would include not just gamma rays but also protons, antiprotons, and positrons. Our satellites, like the Alpha Magnetic Spectrometer on the International Space Station, have been meticulously measuring the flux of these cosmic ray particles. The observed rates of antiprotons and positrons in our galactic neighborhood already place tight limits on how much dark matter decay can be happening. A model that explains the entire gamma-ray background excess would likely overproduce these other particles, conflicting with direct measurements. Furthermore, the very smoothness of the background, while a hallmark of a dark matter origin, also argues against some top-down scenarios. If the signal were coming from localized cosmic strings or other defects, it might create a more granular, patchy glow than what is actually observed. The top-down explanation, therefore, exists in a delicate balance, simultaneously explaining one mysterious feature of the data while being constrained by several others. It remains a compelling, if fringe, possibility, a testament to the fact that when our conventional models struggle, we must be willing to explore the most extraordinary ideas, using the gamma-ray sky as a testing ground for physics that operates at energies far beyond anything we can create on Earth. And so we arrive at the final, and perhaps most profound, mystery that ties all the others together, the ultimate synthesis problem. After this journey through 24 distinct possibilities, from the brilliant jets of blazars to the faint whispers of decaying dark matter, we are left with a crucial realization. It is highly improbable that a single, magical source is responsible for the entire gamma-ray background. The true answer almost certainly lies in a complex cosmic cocktail, a melange of contributions from many, if not all, of the phenomena we have explored. The universe is not so simple as to have only one type of voice. Its chorus is made of countless different singers, each adding their unique tone to the collective hum. The central challenge for modern astrophysics, therefore, is not just to identify the potential singers, but to determine their individual volumes, to measure how much each one contributes to the overall symphony. This monumental task falls to a sophisticated branch of science known as source population modeling, and it is one of the grandest and most difficult puzzles in all of high-energy astrophysics. Imagine trying to recreate the sound of a vast, crowded stadium heard from a great distance. You know the roar is composed of thousands of individual voices, but you cannot distinguish a single one. To understand the sound, you would need a detailed demographic model. You would need to know how many people are in the stadium, how loudly different groups tend to cheer, and how their voices blend together. Astrophysicists face a similar challenge, but on a literally universal scale. Their goal is to build a mathematical model that incorporates every known type of gamma-ray emitter. This model must account for the brilliant blazars, the steady glow of star-forming galaxies, the fading afterglows of gamma-ray bursts, the collective murmur of pulsars, and the potential signals from dark matter and other exotic physics. But it doesn't stop there. The model must also be evolutionary. It has to track how these populations change over billions of years. A star-forming galaxy in the early universe, bursting with youthful vigor, would have been a much brighter gamma-ray source than its older, quieter counterpart today. The rate of stellar explosions and black hole feeding frenzies was far higher in the past. A successful model must faithfully represent this entire cosmic history, simulating the birth, life, and death of gamma-ray sources across 13.8 billion years. The process of building and testing these models is a delicate and iterative dance between theory and observation. Scientists start with our best understanding of each source population. For blazars, they use the luminosity function derived from the thousands that Fermi has resolved. For star-forming galaxies, they use the detailed studies of nearby examples and our knowledge of cosmic star formation rates. They assign each population a predicted gamma-ray luminosity and a distribution across space and time. Then they run the simulation. They add up the light from every hypothesized source at every point in cosmic history and project it onto a simulated sky as it would appear from Earth today. The final step is the critical comparison. Does this synthetic universe, this digital recreation of all known gamma-ray emitters, produce a diffuse glow that matches the actual, observed gamma-ray background in both its total intensity and its intricate pattern of fluctuations? The answer, so far, is a resounding and fascinating not quite. Even the most comprehensive models that sum up all the known astrophysical sources still seem to leave a residual, an excess of gamma rays that remains unaccounted for. This gap is the holy grail of the field. It is the space where discovery awaits. It could be the signature of an entirely unknown class of objects, a subtle error in our understanding of how known sources operate, or most tantalizingly, the long-sought fingerprint of particle dark matter. This synthesis problem is so challenging because it is an inverse problem. We are given the final answer, the observed background, and we must work backwards to determine the ingredients. But there is no single, unique solution. A deficit in one component could be compensated for by a small adjustment in another. Perhaps we have underestimated the number of low-luminosity active galactic nuclei, or overestimated the absorption by extragalactic background light. The only way to break these degeneracies is to bring more data to bear from across the electromagnetic spectrum. The correlation with the radio background, as we discussed, is a powerful cross-check. If a model explains the gamma-ray data but predicts a radio sky that looks nothing like what we observe, it must be discarded. Observations in X-ray, optical, and infrared light all provide independent constraints on the numbers and behaviors of galaxies and black holes throughout history. The synthesis is therefore a truly multi-wavelength endeavor, requiring a cohesive understanding of the universe's entire energetic ecosystem. This grand challenge is more than just an academic exercise in cosmic accounting. Successfully synthesizing the gamma-ray background would mean that we have achieved a complete and accurate inventory of the universe's most violent and energetic phenomena. It would signify that our census of cosmic engines, from the smallest stellar explosions to the most colossal black hole outbursts, is essentially correct. Conversely, a persistent failure to account for the glow would be equally revolutionary, pointing unequivocally toward new physics or a fundamentally missing component in our understanding of the cosmos. The faint, smooth light of the gamma-ray background is therefore the ultimate test of our standard model of cosmology and high-energy astrophysics. It is a canvas upon which the universe has painted a picture of its own history of violence and power. Decoding that picture by patiently and meticulously adding up every possible source of light is the great synthesis problem, a puzzle that pushes our telescopes, our computers, and our imaginations to their absolute limits in our quest to understand the true nature of the universe we inhabit. And so, we have journeyed through 25 profound mysteries, from the unresolved roar of countless blazars to the faint, hypothetical whisper of decaying dark matter. We have seen that this seemingly empty, uniform glow is anything but simple. It is a rich tapestry, a cosmic palimpsest woven from threads of incredible violence and subtle processes. Each thread represents a fundamental question about our universe. Is the background the collective hum of star-forming galaxies, the fossilized echo of gamma-ray burst afterglows, or the steady production of cosmic rays in the vast halos surrounding galaxies? Could it be the signature of primordial black holes evaporating into nothingness, or perhaps even the telltale flicker of action-like particles dancing through intergalactic magnetic fields? Solving these puzzles is not a task for a single telescope or a single theory. It demands a concerted effort across the entire frontier of modern science. We need the next generation of gamma-ray observatories, instruments with even greater sensitivity and resolution to peer deeper into the fog and resolve more of its individual components. We require advanced computer simulations that can model the complex evolution of galaxies, black holes, and cosmic rays across billions of years with unprecedented accuracy. And perhaps most thrillingly, cracking these mysteries may require us to venture beyond our current understanding, to discover new laws of physics that explain the anomalies in our data. The faint gamma-ray glow is more than a signal. It is a direct challenge, a series of riddles posed by the universe itself. The answers we find will not just complete a chapter in an astronomy textbook. They will fundamentally reshape our understanding of reality. Determining the source of this background means uncovering the dominant engines of high-energy power in the cosmos. It means learning whether dark matter is a ghostly particle we can finally touch or something even more strange. It means reading the history of the first stars and black holes from a fossil like they left behind. Every photon in this background has traveled across space and time to bring us a message. We are only just beginning to learn how to listen, so stay curious. The greatest discoveries in our quest to understand the universe's invisible scream are still waiting, just beyond the edge of our current vision, promising to reveal a cosmos far more wondrous and violent than we have ever